data structure called a heap is used for heap sort, and sometimes it's used for other applications, and I'll mention those too as well. So one of the things that we have, first of all, what is a heap? So this is our idea here. Heap is a binary tree. So from the visual standpoint, we can think of a heap as a binary tree, and it has two possibilities as invariant. And of course, you know invariant is a condition which is always true. So an invariant is either greater than invariant or a less than invariant. So if we are looking at a binary tree, is that necessarily a heap? The answer is not necessarily. It has to be a complete binary tree. So for that reason, we need to know what is a complete tree. And that's slightly different than a full tree or a balanced tree, but it's related. So a complete tree is a tree where every level of the binary tree is full, except for the last one, possibly. And if the last one is not full, then the missing nodes must appear only on the right end of that unfinished level. So in this case, you can see that the height of the tree is what? 4, right? The height of the tree is 4, but the depth of 3 is not full. So that means that this is depth 0, depth 1, depth 2, depth 3. Notice there are missing nodes here. The nodes that are missing are this child and the 2 children of all the remaining 3 nodes. But what makes this interesting is that all the nodes that are missing are the rightmost node of that tree. For example, if we had this node added, then this would no longer be a complete tree, because we would not have only the rightmost nodes being missing, because we would have these missing, but then we have a node, and then we have one missing. That's not good. So if we did add a node here, and a node here, for example, then the tree would still be a nice tree, but it wouldn't be complete. We would say the tree is balanced. In fact, the definition of balanced is that all levels are full, except for possibly the last level, with no further restrictions. So you could just add nodes wherever you wanted to and have missing ones at the bottom depth, and that would be a balanced tree, but it wouldn't be complete. And full, of course, means that every level is maximally filled. So in this case, if you want a full tree, you'd have to add 7 more nodes. But the problem with full trees is that you can only have a full tree with a particular number of nodes, and that's specifically 2 to the k minus 1 nodes. Otherwise, you can't have a full tree. So we're not interested in full necessarily, but we're interested in complete. So if we were to expand this tree, which right now has how many nodes? 8 nodes. If we wanted to add a 9th node, it would have to be this one, because if we added any place else, it wouldn't be complete. And if we wanted to go to 10, we have to go to 9, and then we go to 10 here with a left child, 11, 12, 13, 14, 15. If we had 15, we want to go to 16, it'd have to be this node. Get the idea? So a complete tree is restricted in its shape. Okay, any questions on that? Does that make sense? So that's what a complete tree is. So being complete is a matter of shape. So if a tree is either complete or not complete, you can tell visually by inspection. Now, if you look at this tree, notice that the root node has what key value? It's 23. So 23 is, in this case, bigger than the left child and bigger than the right child. Okay? So that would fall into the greater than invariant. So when a parent is greater than either child, we call it a greater than invariant, as long as it is consistent across all subtrees. So if you go to the 11, notice that it's greater than its children. If we go to the 9, it's also true, and 8, it's also true. Okay, so you get the idea. So this is, we have just determined that this is in fact what we call a max heap. A max heap is a heap with greater than invariant. Excuse me, greater than invariant. So notice that we can just fill this out to 15. could add like a 6 here, or a 5 here. Notice the 5 would be a depth 4, even though a 2 is a depth 2. So notice that this greater than invariant for our max heap is not super restrictive. By that I mean, it doesn't give us that much information. For example, if I were to search this tree, looking at the 23, where would I find the 2? And the answer is I don't know. It's not good for searching. Because if I go to the 23, the 2 could be left or right subtree. Notice that here we have a max heap, but the left child is smaller than the right child. But here, the left child is bigger than the right child. And here it's smaller. So it's not a real restrictive search tree at all. It's just a heap. That's what it is. Now, of course, if we had a complete tree and we had the less than invariant, what value would be in the root? 2 would be in the root. So one of the things that the max heap, this one, gives us is what? What absolute information do we have about the set of numbers here? Say again?
Root node is greater than its child.
Yeah, but that's the invariant. But what absolute information do we have over all the numbers? What's the only piece of information that we have over all the numbers? We have the maximum value. If each node is greater than its children, then the root must be the greatest node of them all. And in fact, 23 is the maximum value. If we have a max heap, 23 is the greatest value. Okay? Now, but again, that's one piece of information. Now, do we know where the second greatest value is located? I mean, if I just covered up all the values, if I covered them up, I only showed you the 23, and I just covered up all these numbers here, where's the second greatest value? Well, I don't know where it is, but it's going to be here. It's one of the children. How about the third greatest value? Where am I going to find it? Well, notice that if it's here, if this is the second greatest, the third greatest could be this one, but it also could be that one. So it's not really good for pinpointing things. So why the heck are we studying it? Well, it becomes actually a very, very powerful data structure. So again, the max heap invariant in each node is greater than either child. What I want us to think about is taking this tree and numbering it in what we call row major order. So if we think of the depths as rows, this is row 1, row 2, row 3, row 4, we will number the nodes as they appear, row by row, where the root simply becomes node number 1, the left child becomes 2, the right child becomes 3, the left of the left child becomes 4, 5, 6, 7, 8, like that. So we just order them using a so-called row major order. So the root becomes 1. Now what that gives us, it gives us an interesting relationship between these numbers. And that is we can identify the root as node number 1. So whenever we talk about node number 1, we're talking about the root. Because by definition, we've started our numbering system from 1, on the root, always. Also, we can look at node number I and double it and add 1 to it, and then we'll also immediately produce the left and right children. As you can see here, notice that the left child of 2 is 2 times 2. And 2 times 2 plus 1 is 5, and 2 times 3 is 6, and plus 1 is 7. And if 4, node index at 4, had a right child, that index would be index 9. It doesn't have it. So how many nodes are in this tree? 8. So n is equal to 8. So therefore, if I look at node number 5, how do I know it doesn't have a left child? Because a left child would be index 10. Also, I can find the mathematical formula for the index of the parent node. So for example, if I take 6 and I divide it by 2, I get 3. That's a parent. If I take 4 divided by 2, I get 2. That's a parent. 2 divided by 2 is 1. 5 divided by 2, if I take away the integer part of the remainder, the whole part is 2. 7 divided by 2, if I take the floor function of that, if you will, or I take the integer function of that, that's going to be 3. So I can get to a parent and a child of node I by simply computing it this way. So we can go 2i plus 1 are the children, and then the floor function of I over 2 is the parent. I can also find out the parent which has the highest index in the tree. Well, it's not that difficult. If I just go to n, and in our case n was 8, if I take n, 8 divided by 2, that gives me 4. But it also says that no parent has a higher index than 4. Does that make sense? So if I take the number of nodes in the heap divided by 2, take the floor of that, I can say that no parent has a higher index. So that means the indexes on, the parent indexes on the heap are 1 through the floor of n over 2. Those are the parents. So we're going to talk about a process called max heapify, because it's very nice to look at a heap when the heap is already built. And that's kind of what I showed you right away. I showed you a tree with 8 nodes, and it was a max heap. But what if it wasn't a max heap? How would we create a max heap? What is the process of that? So to do that, we're going to talk about something called max heapify, the process of fixing a near heap back into the invariant. So I don't know why. Let's see. I'm going to show it to you. I don't think the picture really clarifies that. Oh, yes, yes. So here, yes, node 2. So node number 2 has a violation, right? Because if you look at the invariant, notice that here is good, this is going, here is good, this is good, but this is no good. So the question is, how do we correct it? How do we turn this thing back into a heap? So node number 2 has a violation because it's not greater than either of its children. Now, the node index is 2. The number of nodes in the heap is 8. 2 times 2, 4, plus 1 is 5. We know that it has a left and a right child. So we will look at the values at the left child and the right child, which is bigger. 8 is the bigger value. So we're going to swap the 8 and the 3. If we swap the 8 and the 3, then the 8 will be a proper parent for the 6 and the 3 because it will maintain the invariant. But we also moved the 3 into a new position, so we should see whether the 3 has possibly caused another violation, and it will. If you swap the 3 with the 8, then the 8 will go to position 2, the 3 will go to position 4, but then we'll have a violation with what? 7. So we'll swap the 3 and the 7. So you can see the 8, the 3 and the 8 have changed, and finally the 3 goes down. Now, what I want you to think about now is we're going to look at, now that we know that we can compute by indexing the parents and the children of any node in the tree, what I want to do is I want to make a relationship or a mapping from the complete tree to a linear array. And what I will do is I will simply use the row major order to index into the array, assuming that we index into the first element of the array, and that index is number 1. So notice the root becomes the first element at index 1. Its children become 8 and 11, right in a row. 7, 6, 2, 10, 3. 7, 6, 2, 10, 3. Now, why am I thinking of it this way? Because I can. Because now that I have taken this binary tree and moved it in an array, notice that if n is equal to 8, this is 8. If I divide 8 in half, I'm going to get 4. 1, 2, 3, 4. That's the left child. So 7 is the left child of that node, right? Or, sorry, 8 is the parent. 7 is the right child, is the parent of the node. I'm sorry. If I look at the node in position 5, 1, 2, 3, 4, 5, 5 divided by 2, it's going to give me 8 is the node that's the parent. So the advantage of this is that I can process this tree. I can jump between nodes without following any pointers or any references. I can just compute. If I want to know what is the left child and then its right child, so if I want to have the right child of the left child of the root, then I take 1, I double to get the left child, and I double it again, plus 1, I get the right child. I can move throughout this tree simply by indexing. And I always know when I'm not supposed to go there. That's whenever my computed value is greater than n. So heaps are never implemented as trees. Heaps are always implemented as linear structures, arrays. But they truly are trees. And now you probably will understand why they must be complete trees. Because imagine that I would have a left child from node number 5. Imagine if I would have a left child from node number 5. That's perfectly acceptable for a tree, but not for a complete tree. Now, if we allow that to happen, then the number of nodes in the heap would go up to 9. But the index we would expect for the left child here would be 10. Okay? But now if this is 10, that means the number of nodes is 10, but we're missing this one. So now we don't know where the boundaries are, where we have a child, where we don't have a child. So for example, if I had a right child here, its index would be 15. But if the number of nodes in the heap is 9, how am I supposed to know that some of the nodes greater than 8 are not there? It becomes a problem, especially as the heap is growing and getting bigger and bigger and bigger. Because you can see this heap could be very, very large, and oftentimes heaps are quite large. Does that make sense why we use a complete tree? Because a complete tree maps directly into an array. So you can take, so if I take an array, think about it this way. Take an array of 1,000,000 numbers, random values, or just initialize them to random values. I can think of that array of 1,000,000 values as a heap. Now, it's going to have a violation of the invariant, but it's immediately going to have a mapping to a tree, to a complete tree. So if I have 1,000,000 values, the first value is the root. The next 2 are the children. Okay? The next 4 are the left to right children's children. And so with 1,000,000 values, I'm going to end up having about 9 levels of depth, roughly speaking, right? And I can find any node. So now you can say, well, that's very nice. You now have an array, and you're thinking of it as a binary tree structure. Yes, that's true. What does it get me? Well, my goal is going to take this random array of 1,000,000 numbers and turn it into a heap, because it already has a shape, by definition of the mapping function. It already has a shape. So all I have to do is impose the invariant. And if I impose the invariant of 1,000,000 numbers into a max heap, then the root, which will be the first element, will be the maximum element. And then other elements are sort of going to be, they're kind of going to get bigger. Or smaller, I should say, smaller. If that's a max heap, then they're kind of getting smaller. Where we're going to find the smallest element, well, I don't know exactly where, but they're going to tend to be here. We'll talk about those types of issues in a little bit. Because it's actually, the heap gives us a lot of potential homework problems. Good things to think about. And I've given some very good test problems on heaps. So kind of give you an idea of the types of questions that I could ask. But at any rate, that's what we have here. So we're going to look at an algorithm called max heapify algorithm. So given an array A and an index I, we assume that the binary trees rooted at I are max heaps. The binary trees rooted at I are max heaps. But AI may pose a violation to the invariant. Okay? So what is the complexity of max heapify? So keep in mind, the advantage of thinking of the array as a binary tree is that the height of the tree is log base 2. Okay? That's the advantage, that basically where we can play that game. We can play that log base 2 game. So the height of a heap with n nodes is log 2n. That's kind of the advantage that we have here. Specifically, we'll call it the floor of log 2n. So we can swap the node I down to node n, and if you go from I to n, that will be less than log 2n. What we're saying here is swapping a node from position I to position n, which we know is the last position, which is the deepest in the tree. That swapping cannot be any more than log 2n, the height of the tree. Therefore, we're going to say it's going to be less than or equal to log 2n, which is the height of the tree. And of course, the tree is the shape of the heap. So the complexity of the max heapify is theta log n, which is the height of the tree. All right, this next picture, we're going to look at how we're going to turn an array into a heap. So again, we go back to the pictures of trees, keeping in mind that we will not access them as trees with pointers, with references, we will just index them. It's faster. It's like a table type of thing. So the first thing I'm going to do is I'm going to ask you what is the value of n, meaning the number of nodes in the heap, in the tree. It's going to be, what in this one? 8. So what we're going to do is we're going to build the heap from bottom up. So I'm going to take 8 and I'm going to divide it by 2. And that's going to give me, and that's the index of the greatest indexed parent. Because basically, notice that the children, 10, if I look at 10 by itself, that's a heap. It's a heap of 1. If I look at 10, 6, and 6, those are heaps. So I don't have any problems with violations of heaps of size 1, which are leaves. So I want to find the first parent. Well, the first parent, or the last parent, if you will, the parent with the greatest index, is node number what?
7.
In this case, 4. It's going to be 8 divided by 2 is going to be 4. So node number 4. And notice that the blue triangle basically says, I'm going to consider that parent to be the root of the first heap as I build the heap into taller and taller versions of itself. So I look at 7 and 10 and I say to myself, is this a heap? Now, first of all, notice that the shape is definitely a heap. That blue triangle is the shape of a complete tree. It's a tree with 2 nodes where the depth 1, which is the left child, is the left child. So it's perfectly fine. Even if I had 2 children here, this node with the 7 would still be the maximum parent. If this value was, for example, another value. So right now, this is a complete tree. But is it a heap? And the answer is it does not have the max invariant, so therefore what are we going to do? We're going to swap the 10 and the 7. And by doing so, the blue triangle will represent a heap. Or a subheap, if you want to call it that way. And from 4, which is the maximum parent, we're going to move to the next lower index parent, which is 3. Which is a key value of what? What's the key value of node 3? 4. Okay. So what we're going to do is we're going to take the 4, and we know the 4 has an node index of 3, times 2 is 6, plus 1 is 7. So we know it has both children, but it's not bigger than its children. So we'll compare those two, and we'll swap the 10 up. So now we will have the blue triangle and the black triangle will be subheaps. Now what we're going to do is we're going to go to the green triangle, which is rooted at node number 2, which has a 19 currently in it. Notice that 19, we have fixed this to be a heap. We have fixed this piece, so now it's a heap because we have a 10 here, right? This is 6. Now we look at the 19. When we look at the 19, we're saying it's fine, which means that the 19 is a perfectly good parent for a left child of 10 and a right child of 6. And we know going downward, it's fine, because we're fixing it from bottom up, so the bottom is fine. So now we have a subheap with a 10 as the right child of the root, and we have a 19 as the left child. So would you agree that the green heap and the black subheap are both perfectly good max heaps? So now the only thing we have to do is check the last parent, and the least number parent is a root, is 5. So 5 is not as a violation. Now, how much is it going to cost us to swap that 5 into position? Well, it cannot cost us any higher than log 2n. So the first swap is going to be the 5 is going to get exchanged with the, which means we lower it into one level. So 19 becomes the super parent. Okay, the 5 goes to the left, then the 5 is going to be compared against what? The 2 children, which is going to be 6 on the right and 10 on the left, and it's a violation. So we're going to do what? So the 5 is going to get swapped with a 10. And 10 will go in the place where 19 used to be. And 5 will go where the 7 used to be. And finally, what's going to happen with the 5?
Not a violation.
It's another violation. With the, remember which numbers?
It would be 7.
It would be 7, I know. I should be a little more dynamic with this example. Otherwise, you have to use too much imagination. So 7 is kind of sitting here, 5 is coming down here, so now the violation. So the index of 5, when it's in the position of the 7, the index of that is 4. 2 times 4 is 8. So it's the value of its child is a 7. 2 times 4 plus 1 is 9. It doesn't have a right child, so I don't have to compare. So I simply say, is it bigger than its max child? And the answer is no. So I will swap. The 7 will go up again to where it is shown right now, and the 5 will go all the way down there. Notice the 5 went down here. So it went down 1, 2, 3 steps. Notice the height of the tree is basically 4. So you can only go down 3 steps with a height of 4 if you're a root. Okay? So keep that in mind, because I'm going to come back to this. So when you have a tree, no matter how large, and the left subtree of the root is a max heap, and the right subtree of the same tree is also a max heap, then the complexity of turning it into a max heap overall for the whole thing is only going to be LGN, theta LGN, or theta log n. Okay, so now the question is, what we just did, using our imagination, okay, that was a nice example. We had 8 nodes, but what if we had a million nodes? What if we had a million nodes? It's very realistic. Really? Yes, it is very realistic. So if we had a million nodes, then our indexes are 1 to a million. So what is the index? What is the index of the maximum parent? Yeah, it's going to be 500,000. So 500,000 will be the index of the maximum parent. Is that funny? All the other numbers can leave alone. So now we have to see. So now we're going. What's the index of the left child of that parent? Million. Okay. So you have to compare that against. So you're either going to swap it, 500,000 with a million, or not. And then what do? Then you go to 499,999. We're not going to go through all of them, but you get the idea. It seems like it would be a lot of work. Right? So the question is, what's the complexity of doing that? And the answer is, the complexity of building a heap, we can do that by assuming that the tree is full. And by that I mean, not only do we have missing nodes on the right-hand side, we don't have any missing nodes at all, so all levels are full. So instead of having a tree with 8 nodes as we had here, we're going to assume 15. And from 15 we're going to jump to 31, and then we're going to jump to 63. We're going to assume that. For simplicity of analysis. So what we're going to have is, we're going to, look at this, look at the shape of this tree. So we have, this is the 6 at the top has a depth of 0. The number of nodes is 1 because it's a root. And the number of comparisons at that level is 3. What I mean by that is, in order to, the 6, if the 6 is causing a violation, or if this node is causing a violation, it will only be compared at most 3 times. Because the height is 4, which means that it will go from depth 0 at worst to depth 3, which means comparison 1, comparison 2, comparison 3. So number of comparisons, worst case is 3. When we go to depth 1, we have 2 nodes, the 5 and the 4. There are 2 nodes there. And the worst they're going to get comparison in terms of swap down, because we're going to go bottom up. So by the time we attack 5 and 4, they only have a chance to go down 2 units. So depth 1, we have 2 nodes and 2 comparisons. When we go to depth 2, which is the one that has a 4, 2, 9, 2, 10, those nodes, there are 4 of them at a depth of 2, and number of comparisons at most to get them down is 1. By the time we get to the bottom nodes, well, we're going to assume a full tree. We're going to have, in this case, we would have 8 of them. Number of comparisons, 0. Because those nodes, bottom up, are never going to get compared. So, we will do a summation where we'll count from 1 to h, and 1 to h is from 1 to the height. Height is 4, so 1, 2, 3, 4. We will add the number of nodes at depth, I minus 1, times the number of comparison at depth of I minus 1. And the mathematical model looks something like this. So this is going to be, the summation will go from 1 to LGN. Why 1 to LGN? Because those are all of the height levels. Okay, so 1 to LGN. Let's think about what that means. So let's say I is equal to 1. If I is equal to 1, what is 2 to the 1 minus 1? 2 to the 0 is 1. If I is equal to 2, 2 to the 2 minus 1 is 2. Okay, so that 2 is growing how? Exponentially. So it's growing exponentially, yes. And it represents what? The number of nodes at depth I minus 1. Because when I is equal to 1, 2 to the 0 is the number of nodes at depth 0. Okay. So basically, the 2, I minus 1, is representing the number of nodes at all the depths. LGN minus I, LG